Hey, this is Horner, and this is the third section of light, and now we're going to talk about reflection. So specular reflection is the reflection from a smooth, shiny surface. So if you remember before, we were doing diffuse reflection, kind of like when you look at a page. Specular reflection is different because now I have a very reflective surface, so something that's very shiny, like a mirror or a piece of polished metal. And from that, if you take a three-dimensional perspective, you see that the incident and reflected rays are both in a plane that is normal to the surface, which means that it's at a 90-degree angle here. So from here to the surface is about a 90-degree angle, or it should be a 90-degree angle. It's customary to represent reflection with a simpler view. So here we have something called the angle of incidence. That's the light ray coming in. And then the angle of reflection is the light ray coming off. And what we do is we measure from that normal line. The normal line is the line that makes the 90-degree angle with the surface. And then we measure from that normal line over to the reflected or to the incident ray. So a single light ray represents an entire bundle of parallel rays. So we're really oversimplifying things here, but it really helps us keep our figure and all of the analysis clear. The angle of incidence, like we said, is the angle between the incident ray and the normal line. And then the angle of reflection is the angle between the reflected ray and the normal to the surface. The law of reflection basically just says the angle that's going in should be equal to the angle coming out, or the incident angle should be equal to the reflected ray angle. Here's a good example. This says a full-length mirror and a closet door is 2 meters tall. The bottom touches the floor. A bare light bulb hangs 1 meter from the closet door, 0.5 meters above the top of the mirror. How long is this streak of reflected light across the floor is what they want us to find out. So that would be from here to here. So the light hits here, comes back off, and it also goes straight down this way. So we can treat the light bulb as a point source, and we can use the ray model of light. So we only have to think about two rays, the ones that strike the edges of the mirror. So there's one that hits here and comes back. There's another one that comes down to the bottom. All the other rays will be in between the two. So the light ray that strikes the bottom of the mirror reflects from it and hits the floor just where the mirror hits the floor. For this top ray, figure 18.9 has used the law of reflection to set the angle of reflection equal to the angle of incidence. So here's our angle of incidence, and here's our angle of reflection. So the angle going in is right here, and the angle coming out is right here. What's interesting is that angle of incidence is also the same as the angle that we're making with the ceiling itself. So by some simple geometry, the other angles are also equal to that. So from the small triangle at this upper right, we can say the inverse tangent of 0.5 over 1 is equal to 26.6. So now we have the tangent of the angle is equal to 2 over L, or L is equal to 2 over the tangent of the angle. So that's 2 over the tangent of 26.6. So that's about 4 meters. So we now know that since the lower ray struck right at the mirror's base, the total length of that reflected streak, so down here on the bottom, is about 4 meters. QuickCheck 18.3, you're looking at an image of a pencil in a mirror. What do you see in the mirror if the top half of the mirror is covered with a piece of dark paper? So if I cover that, I will still see the full image of the mirror. And it's because if I look at the light rays are still coming in and they're reflecting off, and I'm still able to see the full pencil, even though the light rays look like they should come here and come back, but actually remember they're going in all directions. So we know that there's enough of this mirror here that I can see that pencil. Diffuse reflection is on diffuse reflection here is just on a microscopic scale. The surface of a diffuse reflector, like paper or cloth, is very rough. So this is different than that reflection that we're talking about with a mirror. The law of reflection does still hold, but there's so many of these irregularities that those reflected rays leave in all directions. So it still does follow the law of reflection, but it does it in so many different angles that it doesn't give a very shiny surface here. A plane mirror is a flat mirror, and so rays from point P will reflect according to that law of reflection. The dashed lines here indicate all of the rays appear to have come from this point P prime. So all reflected rays appear to have come from it, even though they don't. They are actually hitting the mirror and then bouncing back. So this reflected ray, if you notice, when it comes in, when it's reflected, it looks like it's coming from back here. When we do some ray diagrams, this will make a little bit more sense. This is what we call a virtual image, and because it is appearing that all those light rays are coming from behind the mirror. And so there's actually no light rays coming from that. They're just all coming from the mirror and then hitting your eye. But because it looks like it's coming from here and not actually from the object, we do call that a virtual image. The image distance is equal to the object distance, so however far your hand is, it looks like it's at the same distance behind the mirror. So as long as it's a flat mirror, it does it. If this guy's a meter away, his reflection looks like it's a mirror away, looks like it's a meter away on the other side. The eye does a very good job of capturing and focusing all those divergent bundles of rays from each point of the image, and we see that extended object. So pretty nice thing that your eye can do. These are some rules that kind of happen. We're going to go through all of these rules, so I'll let you take a look at those on your own. An object is placed in front of a mirror for QuickCheck 18.4. The observer is positioned as shown. Which of the points best indicates where the observer would perceive the image? So remember, we have our light coming in, it's hitting the mirror, and then coming back. So a lot of people pick A. Unfortunately, that's not the right answer. It actually looks like it's way down here where the object is. But in reality, the light is hitting here and then coming back, because remember, the angle in should be equal to the angle out. So the object doesn't appear here, but that's where all those light rays will hit and then bounce back to the observer. For this next one, they want to know how high is the mirror. So if your height is h, they want to know how long does the mirror need to be in order for you to see your entire body. So if we use the ray model of light, we can actually see this, and we only need to consider that we have to have two rays leave the top of my head and reflect and come back, and the same thing with my feet. So I just need to see the top of my head come back and my feet. And you'll notice that the shortest mirror that you can use is actually about 1/2 here of the length of your body. So if your body is this high, then you only need about half of that to see your entire body for your height. So this goes through this just a little bit more, and I'll let you read all those things if you want to actually go through and do that. And that is the end of the reflection section. There are also some notes there on going through and doing ray diagrams, and we will work on those next. So this is where we start talking about image formation, and we're going to, instead of using flat mirrors like we've been doing, we're going to start using curved mirrors. So spherical mirrors are curved mirrors, and they can be used to form different images. The one that we see here is concave, because it's kind of like looking into a cave. If you were standing here and you're looking, you would be looking into a cave. So all of the light rays that hit it are redirected and come back, and they actually hit this little point here, and we call that the focal point. This mirror is different. It's convex, so instead of looking into a cave, you're looking at the back side of the cave, is what some people think of. So that is a convex mirror, and all of the light rays, instead of hitting it and bouncing towards you, bounce away. So they actually bounce back at an angle away from that line that's coming into it, and that makes an object look like it's on the other side of the mirror or behind the mirror. For concave mirrors, these parallel rays do come in, they come back, and they hit this called the focal point. The rays passing through the focal point will reflect from a concave mirror, and they will emerge parallel. So if I start here and shine light to it, they come back and they will go parallel. So any ray passing through a focal point after reflection emerge parallel to the optical axis. For concave mirrors, the law of reflection says any incoming ray will reflect at the same angle, but on the opposite side of the axis. So same type of thing we've been doing before. And when an object's distance s from the mirror is greater than the focal length, there are 3 special rays that are enough to locate the size and position. So here are our special rays. We just need one that is parallel. We need one that is going through the middle of the lens or through the mirror. And then we need one more ray here that's going through the focal point. If I trace those 3 rays, I can actually tell where the image will be. The image here is called a real image because it's on the same side of the mirror. It doesn't appear on the opposite side of the mirror. If the object is inside the focal point, then we're going to call that a virtual image. So if I move this object to the middle, as we do some of these things in the lab, that will make a lot more sense. These are some really important things that you can do in order to do what we call ray tracing. And like I said, we will do those actually in class because they're a lot easier to do. This is the section where we would do that, so I'm going to stop at this point.